All right, welcome back to another episode of Science with Surbeck. Today what we're going to be talking about is section 12.3, which deals with limiting reactants. Now before we get into the details of these notes, there's a couple of objectives I want you to be able to do by the end of this video. Objective number 1, identify the limiting reactant in a chemical reaction. Objective number 2, identify the excess reactant and calculate the amount remaining after the reaction is complete. And objective number 3, calculate the mass of a product when the amounts of more than one reactant are given. All right, so let's start out here with a basic definition of what a limiting reactant is. So a limiting reactant is the reactant in a chemical reaction that is completely consumed in that chemical reaction. Now, by having a limiting reactant, what it does is it does a couple of things. One, it limits the extent of the reaction. And what I mean by the extent of the reaction is once the limiting reactant is gone, the reaction, the chemical equation or reaction can no longer proceed. What it also does is it determines the amount of product that is produced. So some things to keep in mind about chemical reactions. Chemical reactions are going to proceed until all of one reactant is used up. And then generally, once we have the limiting reactant, once all of that is gone from our reaction, generally you're going to have one or more reactants that are in excess. Now, an excess reactant is the reactant or reactants that remain unreacted after the reaction stops. Now, another thing to keep in mind is that rarely in nature, so in chemical reactions that occur on their own in nature, the reactants in a chemical reaction are present in the exact ratios specified by the balanced equation. Okay, so now we have an introduction to what a limiting reactant is. And remember, this is the reactant that is completely consumed in a chemical reaction. Okay, so to get you into the mindset of what a limiting reactant is, I have a real generic example. And this example, again, has nothing to do with a balanced chemical equation, but it utilizes that concept of limiting reactant. Okay, so we have here a tool set that needs to consist of 2 screwdrivers, 1 pair of pliers, and 1 hammer. From the picture below, we want to know how many sets of tools, these tool sets, can be made. So what I'm going to do is I'm just going to circle this out in my red marker, and we are going to make our tool sets. So I'm going to say right here, this is going to be my complete tool sets, and I'm just going to make a count of what these tool sets are. Okay, so remember, in each of these tool sets, I need 2 screwdrivers. So initially here, I am just going to circle out 2 screwdrivers. I'm going to say they're gone because they're in a set. I need 1 pair of pliers. They're gone. And I need 1 hammer. They're gone. All right. So by doing that, I put those 4 things together and I've made 1 complete tool set. Now I'm going to do the same thing. So again, in my second set, I need 2 screwdrivers. I need 1 pair of pliers, and I need 1 hammer. Again, I put those all in their own individual set, and so I obtain another set. So let's go try to make a third set. So again, we need 2 screwdrivers, we need 1 pair of pliers, and we need 1 hammer. So that's our third set that we've made here. And now let's keep making our sets. So we need 2 screwdrivers, 1 pair of pliers, and a hammer. So that's our fourth set right here. And then we have to look at this, okay? And we look and we say, okay, each set needs 2 pairs of screwdrivers, a pair of pliers, and a hammer. But do we have another hammer to make that 5th complete set? Well, the answer is no. So our limiting reactant in this example here is our hammer, because we ran out of hammers. We ran out of hammers prior to making that 5th set. It was the first thing to run out. So that hammer is our limiting reactant. Now, what we also have to be concerned about is our excess reactants. So in this case, we're actually going to have 2 excess reactants, and the first of which would be our first thing that is listed. Okay, so right here, we have 2 screwdrivers that are left over, and so we would have 2 screwdrivers that are left over. They're not utilized to make a complete tool set. What we also have is 1 pair of pliers, and that would be our other reactant that is used up. So we can see here, we can apply this concept of limiting reactants to a basic example like we have here. All right, so now let's go back into chemistry and let's learn how we can actually calculate the limiting reactant. All right, so we want to know how we can calculate the limiting reactant. And it's essentially the same steps that we have been doing, but we're going to have to do it for 2 of the reactants that are given. So the first step, just like we always have done, is balance the chemical equation. And then the second step is write down what is given. Now, there will be 2 things given, 2 reactants given. So you actually have to do step 2 twice. Now, this third step is you need to convert all reactants to grams of a desired product. Now, this is going to require 3 things. The first thing it's going to require is the molar mass of the substance given. It also requires the mole ratio between the reactant and the desired product. And then it also requires the molar mass of that product you are converting to. And then the fourth step is to determine which reactant produced the least amount of product. And whichever reactant produces that least amount of product, that is our limiting reactant. Now, I want to take the time here to make a quick note, and that is this. The amount of product determined from the least amount of product is also the amount of product produced with a reaction involving a limiting reactant. All right, I know that note's kind of confusing here, and I just want to note this. The LR is the abbreviation we're going to utilize for limiting reactants. All right, so I know this is a lot of steps, but I want to go through these steps in our next example problem. Okay, so in our example problem here, it says use the chemical equation below to determine the limiting and excess reactant when 200.0 grams of sulfur reacts with 100.0 grams of chlorine. Now, I went ahead to help us out here and I provided the molar masses of each and every substance here. The first thing, again, whenever you get to a chemical equation, you need to make sure it's balanced, and if it's not, go ahead and balance it. So right now we have 8 sulfurs on our left, and over here on the right we have 2. So to get this right side up to 8, we need to put a coefficient of 4. Now we go to our chlorines. We have 2 on our left, and now we have 4 times 2 on our right, so we have 8. So we need to put a coefficient of 4. Now we do step 2. This is saying write down what is given. Now we're given 2 things, and we're going to have to write down 2 things and make our proper conversions. So we have this. We have 200 grams of sulfur, S8. And so 200 grams of sulfur is going to be the first thing that we write down. Now I'm going to start out this conversion factor here, but I'm going to give a little bit of space because we also have another substance, another reactant that we have to write down. So we also have 100 grams of chlorine. And so we're going to write down 100.0 grams of chlorine. And I'll start out the conversion factor. We're going to come back to it. But we are going to have to convert these to a certain product. So I'm going to do this one at a time. I'm going to convert S8 to our desired product, and then I'm going to convert chlorine to that same product. Now, what product do I choose? Well, if I blank out the reactants here, we only have one product. Sometimes you'll have to choose, and it doesn't matter as long as you convert to the same product. Now, in our final example of these notes, we will go through a problem where we will have to choose, and I'll walk you through that process. But the first thing that we have to do is we have to get rid of grams of S8, and we have to go to moles of S8. Okay? And so, mole over gram or gram over mole, we turn to the molar mass. The molar mass has a molar mass of 256.56. So that becomes what we put with grams, 256.56 grams of S8 per 1 mole. Now we have to have our next conversion, and again we're going to get rid of moles of S8, and on top, remember we're trying to get to grams of our product here, but we can't do that in one solid step here or one sweep. So we're going to go to moles of S2Cl2. Now remember, mole over mole. Where we get our values here is from our balanced chemical equation. So the coefficient in front of S8 is 1. So we put a 1 with S8. And then the coefficient in front of S2Cl2 is 4. Now, again, we need our substance, our product, in grams because we don't have a mole scale. It'd be nice if we did, but we have to measure this in grams. So we need to go one step further, and we need to go from moles of S2Cl2 to grams, okay? Now, again, gram over mole. We turn to the periodic table and we look at our molar mass. The molar mass of S2Cl2 is 135.04 gram per mole. That number is associated with grams, so 135.04 gram per 1 mole. Now what we need to do is calculate this out. So what I'm going to do here is I'm going to take 200.0 times 1 times 4 times 135.04 and divide it by everything on bottom. So we get 200.0 times 1 times 4 times 135.04. Close my parenthesis, I press enter. I divide it by 256.56 times 1, close my parentheses, and I get a value of 421.1 grams of S2Cl2. So this top part here, again, equals 421.1 grams of S2Cl2. Now that doesn't necessarily mean this is our answer because we have to go through this process with our other reactant, okay? So with this here, we're going to do very similar steps, but we are going to utilize chlorine as our starting substance, and we're going to convert to the same product. So we're going to cancel out grams of Cl2 on bottom. On top, we're going to go to moles Cl2. Now, mole over gram, gram over mole, we turn to the periodic table. Molar mass of chlorine is 70.9 grams per mole. So the 70.9 is associated with grams, and that is for every 1 mole. Now, we need to go from moles of Cl2 and convert to that same substance, which is going to be S2Cl2, okay? But we can only convert from moles to moles of one other substance, okay? So we have to do mole to mole. That is very, very crucial in what we're finding. Mole over mole, we turn to the periodic table, or we turn to the balance equation. We have a coefficient of 4 in front of Cl2, so that means we put a 4 in front of Cl2. And we also have a coefficient of 4 in front of S2Cl2, so we put a coefficient of 4. Now, what we do here is we need to get it into grams of S2Cl2. So we cancel out moles of S2Cl2, and we put grams of S2Cl2 on top. Now, gram over mole, we turn to the molar mass of S2Cl2, which is 135.04. That number is associated with grams, and that's for every 1 mole. So now we can do a calculation. So what I'm going to do is 100 times 1 times 4 times 135.04 divided by 70.9 times 4 times 1. So again, 100.0 times 1 times 4 times 135.04. Close my parentheses. Now, I divide by everything that's on bottom. So 70.9 times 4 times 1. Close the parentheses. I press enter. And rounding to this 1 decimal here, I get a value of 190.5 grams. So 190.5 grams of S2Cl2. Okay, so here is a very crucial step that we just have to think about. We've done a lot of work in this problem so far, and so what we need to do is ask ourselves, what number is smaller, 421.1 or 190.5? Well, 190.5 is definitely significantly smaller. This means whatever produces that smaller number, this means that starting substance is our limiting reactant. So in this case here, our limiting reactant, LR, is Cl2 because that is the substance that produced the smallest amount of product. This means that our excess reactant is the other substance, which is S8 in this case. So our excess reactant is S8, our sulfur, okay? And now we can determine how much product was produced. So the amount of S2Cl2 produced is equal to the smallest number that we calculated. And we've already said the 190 number is our smallest number. So this means that we produced, in this reaction, if everything goes okay, we produce 190.5 grams of S2Cl2. It's the smaller of those numbers. So again, just to recap, the smaller of the numbers, whatever started out, the substance that started that out, is our limiting reactant. The other substance is the excess reactant. So you got to put your thinking cap on a little bit once we get to this portion here where we've done and utilized the calculations. Now, let's go one step further and let's figure out, okay, what happens if we want to determine the amount of product of S2Cl2 produced. So I'm going to write down the steps here in just a second. Okay, so To produce this or to go through this product here, step number 1 is determine the limiting reactant of the reaction. And then we have to put our thinking cap on. We've done this in our previous example. But whatever reactant produces the least amount of product is the amount of product produced in a reaction involving a limiting reactant. Okay, a couple key things here. This is the least amount of product produced, okay? This right here is crucial to our success here. And this is our thinking cap that we need to be aware of. So let's go through and let's do another example. All right, so this is the same example that we just utilized. So to emphasize this step, what I'm going to do, remember we balanced it by having a coefficient of 4 in front of the Cl2 and S2Cl2. And what I'm going to do, because we've already done this, I'm going to write out and use our previous example, the one we did just a few moments ago, and I'm going to put this information on our sheet. So I'm going to balance this, or I'm going to pause the video and write down what we just had. All right, so again, this was the same exact problem that we had, and we went over it. So to determine the amount of product produced, the first step is determining the limiting reactant. So again, we put on our thinking caps, and we ask ourselves, which of these values, 421.1 or 190.5, is smaller? Well, the 195.5 is smaller. This means the substance that produced that smaller number is the limiting reactant. So again, the limiting reactant is going to be our Cl2. Now, whatever substance is the limiting reactant, that value produced is the amount of product that can be produced. So, in this case, the amount of S2Cl2 produced is 190.5. And then, just a reminder, whatever substance is not Cl2, in this case S8, that is our excess reactant. So, very similar thing that we have just done here as we did in the first problem. And I want to emphasize that doing it like this, I know it's a lot of work to go from grams of one substance to grams of one product, and you do it twice, but you knock out 3 major things. You find out the limiting reactant, the excess reactant, and the amount of product that can be produced. Okay, so let's go one step further and let's go through this particular problem and figure out, okay, well, S8, if this is excess reactant, we should have some S8 that is not reacted at the end of the reaction. So let's go through, let's utilize some steps to go through that process. All right, so to figure out how much excess reactant is remaining, the first thing you need to do is determine the limiting reactant of the reaction. The second thing that you need to do is convert the grams of the limiting reactant to grams of the excess reactant. Then, once you've done this, what you're doing here is you're finding out how many grams of excess reactant are actually used. So then once you find out how many grams of excess reactant are actually needed, what you need to do is you need to subtract the number of grams of the excess reactant needed from the number of grams given of the excess reactant. So to help you out here, a formula here for number 3 is as follows. So the formula is the number of grams excess reactant remaining is equal to the number of grams excess reactant given minus the number of grams excess reactant needed. Okay, and this will be a little bit easier to see in our example problem. So let's go through this and let's utilize the same problem that we've been using. So we go through the same problem. We have 200 grams of sulfur reacting with 100 grams of chlorine to go through this particular equation. Remember, we balanced the equation, and now we've done this problem. So I'm not going to take the time to write this down, but I'm going to identify this. Our excess reactant is our S8, okay? And our limiting reactant is our chlorine, or Cl2. And again, I'm not going over this because we've already done this problem. You can reference back in notes what we did mathematically to determine that Cl2 was the limiting reactant. Now, the steps that we just went over to find out how much S8 remains after the reaction goes by is this. We do a very unique step where we convert the amount of limiting reactant to excess reactant. So we start out here with how much limiting reactant that we started with, which was 100 grams. And this is 100 grams of Cl2. Now, we convert this to grams of sulfur. Just so we know our molar masses. Remember, I gave them to you in the previous problem, but the molar mass of chlorine is 70.9 grams per mole, and S8, the molar mass of S8 is 256.56 grams per mole. Okay, so keep those numbers in mind as we go through this. So the first thing that we have to do, we're converting grams of Cl2 to grams of sulfur. So we cancel out grams on bottom of Cl2, and we go first to moles of Cl2. So the molar mass of chlorine is 70.9. In this case, it will go on bottom. That's for every 1 mole. Then we cancel out moles of Cl2, and we are going, very important, we're going to that excess reactant. So we need to go to moles of S8. We turn to the balanced chemical equation. We see there's a 4 coefficient in front of Cl2 and a coefficient of 1 for S8. Now again, we don't have a scale that measures in moles, so we have to convert moles of S8 to grams of S8. Now, the molar mass is 256.56 grams per mole. This number goes with grams here in our conversion, and that's for every 1 mole. Now what we're going to do, we're going to get our calculators, and I'm going to take 100.0 times 1 times 1 times 256.56. Close my parentheses. I'm going to divide it by everything that is on bottom. So I divide it by 70.9 times 4 times 1. Close my parentheses. And I get a value of 90.5, by the time I round, 90.5 grams of S8. So this is 90.5 grams of S8. And this is important. I'm going to label this. This is how much S8 is used in the reaction. But the problem says, all right, determine the amount of excess reactant. So we want to know if we use this much excess reactant, we want to know how much S8 remains. So what I'm going to do here, amount of S8 remaining after the reaction goes through, we need to figure out how much S8 is remaining. So what we do, we always put out the amount we started with of sulfur. In this case, it was 200.0 grams of S8, that excess reactant. We utilize 90.5 grams of S8. So we're going to subtract out what we used to find out what is remaining. Okay, so in my calculator, I'm going to take 200.0 minus 90.5. And I get a value of 109.5. So this right here, 109.5 grams of S8 is amount of excess reactant remaining. Okay, so a lot of things went into this to be able to get our final answer of 109.5 grams of excess reactant, in this case S8, remaining. All right, so what we're going to do, we're going to transition and we're going to do a problem from start to finish, talking about limiting reactant and figuring out how much excess reactant remains. Okay, so we'll transition here. All right, so again, this is a limiting reactant problem from start to finish. Obviously, it's a different problem than what we have been utilizing. But the first thing that we always have to do is balance our chemical equation. So we start out here with our phosphorus. We have 4 phosphoruses on the left, 4 on the right, so we're good to go. Oxygens, we have 2 here, we have 10 here, so we need to put a coefficient of 5. Now, to help you out here, I'm going to save some time and I'm going to give you the molar masses of each of these substances. So the molar mass of P4 is 123.88 gram per mole. The molar mass of oxygen is 32.00 gram per mole. And the molar mass of tetraphosphorus decoxide is 283.88. And that is grams per mole. Now, the first problem says here, determine the mass of tetraphosphorus decoxide formed if 25.0 grams of phosphorus and 50 grams of oxygen are combined. Okay? So what we must do, remember, we have to write down each of our starting substances. We have 2. So we have 25 grams, 25.0 grams of phosphorus, P4, And we also, I'm going to start out with the conversion, we also have 50 grams of oxygen, O2. Okay, now we need to convert to the mass of our product. So we're going to eventually get to grams of tetraphosphorus decoxide. Okay, so what we need to do first, we're going to convert grams of P4 into moles of P4. All right, so moles of P4. So we have 123.88 for every 1 mole. Now we got to go from moles of P4 to moles of P4O10. We can't go straight to grams. We have to go moles of one thing to moles of another. So what we do to find out our values here is we look at our coefficients in our balanced chemical equation. So for our coefficient of P4, we have 1. And for the coefficient of P4O10, we also have 1. Now, we need to get this to grams because we don't have a magical mole scale. Wish we did. But we go from moles of P4O10 to grams of P4O10. We utilize the molar mass here, which is 283.88. So I put 283.88 for every 1 mole. Now I go and I calculate this right here. So I'm going to take 25.0 times 1 times 1 times 283.88 divided by 123.88 times 1 times 1. So we have 25.0 times 1 times 1 times 283.88. Press enter. I divide this by 123.88 times 1 times 1. I press enter. I get a value to 3 significant digits of 57.3 grams of P4O10. Okay, now what we need to do, we need to convert grams of O2 and get it to grams of P4O10 to compare. So the first thing that we do is we cancel out grams of O2 and we get to units of moles of O2. So the molar mass of oxygen is 32.00 grams per mole. So I'm going to put 32.00 grams for every 1 mole. Now I need to go moles of oxygen to moles of P4O10. And again, we can't go moles of oxygen to grams of P4O10. We have to go through this step. So the coefficient of oxygen is 5. The coefficient in front of P4O10 is 1. And then we have to do one final step. We have to divide moles or cancel out moles of P4O10 and go to grams of P4O10. We utilize the molar mass, which is 283.88, and so we have 283.88 grams for every 1 mole. Now we can go ahead and calculate it. So we're going to take 50.0 times 1 times 1 times 283.88, divide it by 32.00 times 5 times 1. So 50.0 times 1 times 1 times 283.88. Close the parenthesis. We divide that value there. So we divide by parenthesis 32.00 times 5 times 1. We press enter. We get a value of 88.7 grams of P4, 88.7 grams of P4O10. Okay, now we ask ourselves, which of these two numbers is smaller, 57.3 or 88.7? Well, the 57.3 is the smaller amount. So what that means for our answer is that 57.3 grams of P4O10 is produced. Okay, now I want to go one step further. I know the question doesn't ask this, but the substance that produces the smaller number, in this case 57.3, the substance that we started out with, that is our limiting reactant. So P4 is the limiting reactant. I'm going to abbreviate that LR. And that means oxygen, O2 is the excess reactant. And I'm going to abbreviate that ER. Okay, so that right here is our answer. I know it's a lot of work to go from start to finish here, but we have answered a lot of questions in this example. Now we got to go a little bit further, and we want to know how much excess reactant remains after the reaction stops. So in our steps, we always start with the limiting reactant, which is P4. And we are going to do this. We are going to convert 25.0 grams of P4 to grams of O2. Okay, so how we do this, we go and we cancel out grams of P4 and we go to moles of P4. So mole over gram, we turn to the molar mass, which is 123.88 per 1 mole. Then we need to cancel out moles of P4 and we need to go to moles of O2. Again, you're converting your limiting to your excess. We find out our mole ratio. So our mole ratio here is 1 mole of P4 to 5 moles of O2. And then we need to convert moles of O2. We need to convert moles of O2 to grams of O2. So the number of grams of O2 is 32.00 grams per 1 mole. All right, so now we need to do a little converting here. We're going to take 25 times 1 times 5 times 32 divided by 123.88 times 1 times 1. So 25.0 times 1 times 5 times 32.00. Press enter. We divide it by 123.88 times 1 times 1. Close the parentheses. We get a value of 32.3. So this is 32.3 grams O2 used in reaction. To find out how much excess remains, what we need to do, we need to subtract from the starting amount of oxygen, the excess. So we had 50 grams to start out with of O2. We used 32.3 grams of O2. So 32.3 grams of O2. And then we just perform this on our calculator. So we do 50.0 minus 32.3. We press enter. And that's a value of 17.7 grams of excess oxygen. And I know that's a lot of steps, but that is start to finish how we would find out how many grams of product we produce, what is the limiting and excess reactant, and how to find out how much excess reactant remains. All right, so that was our last example. We have just a few more points I want to make about limiting reactants. All right, so you may be wondering, why use exact mole ratios in a chemical reaction, or why might it not work? So the first things that we need to think about here is this. Some reactions do not continue until all the reactants are used up. And so if this happens, some chemical reactions appear to stop while portions of the reactants are still present in the reaction mixture. All right, so if we conduct a reaction in this way where we use exact mole ratios, this is a very inefficient and wasteful way for our reactions to proceed. All right, so now what we're going to transition to is how can we reduce that waste? If we can't use exact mole ratios, well, how can we reduce the waste here? And so what they have done, what chemists have done, is that they've found by using an excess of one reactant, it reduces the wastefulness and inefficiency of a chemical reaction. Now, what we can do here is that we can have reactions can be driven to continue or continue until all of the limiting reactant is used up. And usually what they do is they use the least expensive reactant to be this excess reactant. So by having an excess reactant and choosing it wisely or choosing that one usually that's more cost effective, what happens is that this can also help speed up a reaction, which can make it a reaction more efficient. Now, a few examples of this are as follows. Number one here is the amount of oxygen in a Bunsen burner. And number two is the production of polyvinyl chloride, or PVC. All right, so I know this is kind of a lengthy episode here, but there was a lot of chemistry discussed in our concepts of limiting reactants. The key thing there is converting to the correct product and making sure you do that for both substances involved. Once you do that and you go through the calculation correctly, everything else is just thinking about how the reaction happened and what is the systematic approach to how we find the limiting and excess reactant. All right, so I hope you have enjoyed this episode. And as always, if you haven't already, make sure you subscribe.